Okay, what we're going to look at here is how to calculate a good old t-test. And the example that I'm going to use is the one on page 175. At least it starts on page 175 in the book. And for those of you who remember seeing it, it is the one in which you are comparing two offices and the time that it takes to clear problems from customers' telephone lines. So if you pull that up, it will be helpful while you're doing this. So it goes on page 175 and 176. And the t-test is asking, is there evidence of a difference in the mean waiting time between the two offices at a level of significance of 5%, 0.05? Now this is a pooled t-test because these are two independent groups. For example, we're not trying to pair one office with another or look at an office before an intervention or after an intervention, in which the two groups would arguably excuse me, not be independent, so that you would use a paired t-test. So I wrote down, you're not trying to compare differences between any particular calls. These are calls. Each one of these is a call and how long it takes to clear the problem. So for example, this is, say, Central Office 1, and it took 1.5 minutes to clear the problem that the customer was experiencing. And here's another random phone call that was evaluated in Office 2, and it took almost 8 minutes for the time to be cleared. So you can see I put down here is the variance, and here is the average time. So here are the two means. So if you look, I put up here average in parentheses A1, cell A1 through A20. And you can see that the means are 2.214 and 2.01. So it takes 2.2 minutes on average for Central Office 1 to clear a problem and 2 minutes for Central Office 2 to clear the problem. So in order, again, remember that a t-test is intended to compare two groups and their means. So I wanted you to see the means as we started. So this calculation is actually in the book, but I wanted to create it for you. So first, in order to create a t-test, you'd need to calculate the pooled estimate of the population variance. And in this particular case, the variance for this office is 2.95, and the variance for this one is 3.57. Now, if you don't remember how to do a variance, let's go back to how to calculate standard deviation. And remember that this is in another video that I just posted for you. And let's go through it very quickly. So say this were, in this case, well, I'm not even going to label what the data are. But if you look, here is the mean for a set of, I believe this is 10. Let's check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points of data. And to create the variance, you would have to look at each data point and how far it essentially varies from the mean. And then look at the total degree of variance among all data points compared to the mean. Because remember that standard deviation is intended to tell you how much variation you have in data. So in this case, you would subtract 4, this data point, minus the mean. 4 minus 61.2, you get negative 57.2, and you would square it. You'd multiply it times itself. So if you can see in that square of difference, it's cell F6 times cell F6. And that is F6 right here. Then you take this data point, 100 minus the mean, 61.2. 100 minus 61.2 is 38.8. You multiply 38.8 times itself, and you get 1,505. Again, the idea here is to notice that these numbers are reasonably big because even if you just look at the data here, there's a good degree of variety here. It's not like everything kind of hangs toward the mean, which is 61. You've got 4 and 100 versus look at this data set, you've got 61 and 60. And so those numbers generally are in the 50s, mostly in the 60s, and they all kind of hang around the mean. So you're not going to have as much variation in that versus this. And the variance, again, is one of the ways to calculate the level of dispersion in the data. So going back, you square the difference for all data points and then add them up. to get the sum of the squares, which in this case is 20,000. Now compare that to this one, which has, as you can just look at it, very little variation in the data versus the mean, 105. So you can already see it's a lot different. Now the variance is simply the sum of the squares divided by the number of data points values minus 1. So remember, we had 10 data points, minus 1 is 9, so you divide 20,777.6 divided by 9, and you would get the variance. Okay, and that is how you calculate it. So it's really not all that tough. So what you'd be doing in this case is you would get the mean, which is 2.214, and then go through the same kind of calculation. Take each data point and look at how far away it varies from the mean, square it, add them up, and divide it by the number of data points, in this case 20 minus 1, which is 19. So in this case, you got 2.95 for this particular group, and 3.57 for this particular group. Hope you can see that. So the chi-squared test, let's see, excuse me, what are we doing here? Oh, I'm sorry, okay, so we get the variance. Now we've got to get the pooled estimate of the variance. So we have the variances for each of the data sets. So now all we do is get the pooled estimate of the variance right here. And that equals the degrees of freedom for one sample, which is 19. Remember, one sample is 20, and you get minus 1 is the degrees of freedom, times the variance for that sample. So this is the beginning of this equation right here, 19 times 2.95 variance, plus the degrees of freedom for the second sample, which is also 19, and that sample's variance over here, 3.57, divided by the total sample degrees of freedom, which is 38. So you would multiply these two, add them to the multiplicative value of these two, and divide by the sample degrees of freedom, which is 3.38. So the statistic comes out to 3.265. Now, once you have the pooled estimate of the population variance, you can calculate the t-statistic. So that number equals 2.214, which is the mean. You're basically looking at the difference in the means here. 2.214 minus 2.0115 divided by the square root. So remember, the square root looks like this. I'll make that, but I couldn't figure out how to do it on Excel. Of 3.266 times 1/20th plus 1/20th. So you look at that, you'd add it up, it's 2/20ths or 1/10. So 3.266 times 1/10, and look at the square root of that. So if you then, taking these two down, the difference between these is 0.2025 divided by 0.5714. The test statistic equals 0.3543. Now, when you compare that to the critical value and of 2.0244, you see that the test statistic for these samples suggests there's not enough evidence to reject the null hypothesis, because it's not far enough above, or it's actually far below the critical value, which suggests that the population mean is close to the other population mean or sample mean. So there's not enough evidence to reject the null hypothesis. There's not enough evidence to reject that the waiting time between these two offices is different. And even just intuitively looking at these, it doesn't look like there would be that likely with 20 data points that you'd find a big difference between these two. Now, the critical value for this statistic, just for those who are interested, is found in the back. The appendices has a list of tables, and you'll notice the tables are for each of the major statistics that we've covered in this class on how you find critical values. So, for example, in page 320 and 321, you can calculate the critical values for the chi-square test. On page 317, starting on page 317, you find critical values for t. And so if you look the t-value, the test statistic critical value is found on page 317 under 0.025. It's a two-tailed test, remember, because all you were doing is trying to figure out whether there's a difference, and that could be higher or lower, directional. If you were trying to hypothesize that one is higher than the other, then it would be a one-tailed test, and you would put, if you were looking at a level of significance of 0.05, you'd put everything in that tail, so it'd be 0.05. In this case, because you're looking at directions in both ways, you have to divide the 0.05 in half. So you get 0.025, which is on the left-hand side of the page on 317, and you go down to the number, the degrees of freedom, which in this case is 40 minus 2. So for each one of these samples, it's 20, and you would take away 1. And so you pool those, and you have 40, total data points of 40, minus 2 is 38 degrees of freedom. So if you travel down the page to 38, you will find, oh, I'm sorry. So 0.025 is the fourth column over. And if you follow that down to 38 degrees of freedom, you will find 2.0244. So this was just another way to get you to realize how these calculations are conducted. And one alternative, of course, is to simply go into the Excel alternative and choose two samples assuming equal variance, which is the t-test for this. So let me see if I have it on here for the day. I may not actually have it on this one. I don't have it on here. It would show you data analysis over here. But I did run a t-test using Excel for you. And you could see here are the Excel results. And the t-statistic 0.354 matches what we just did here. And you see the critical value of 2.0244 automatically pops up when you do a test statistic like this. And here are the means. Here's the variance that that I explained how to do. Here are the various, quote, observations within the samples, and so forth. So this is not really that tough to calculate, as you can see. However, I think that once you understand generally what's going on here, it probably would lead most of you to the feeling that, cool, I can just frankly rely on Excel and other programs to do this for me. The other thing that I would want to mention is, one more time, that the reason that I show you the critical value is because I mentioned multiple times that there are two ways to evaluate any statistic. One is by looking at the p-value, which is really, frankly, the one that I would highly recommend that you consider going forward. Or you could use the critical value, and it will always pop up for you. See, there's the critical value, t-test, critical one way, one tail, two tail, and then what you would actually get in terms of your actual statistic. Excuse me, there's the t-statistic. So this pops out the critical value that you'd be looking for every time. So there's no real need to actually go back to look at it under the tables and calculate it. All right, on to the next video.